So our next speaker is from one of the two areas that have been impacted the most by machine learning and AI recently, which is namely vision. So this is Fredrik Kahl, who is the professor in the new electrical engineering department and leads the machine vision, computer vision group. And he leads many big projects in that area. And we'll look forward to hearing about how deep learning has completely changed this field. Pull it out and pull it. Ah, something happened. Yeah, there we go. Just took some time to. Always nervous with equipment problems in such situations, but it works now.
All right.
Machines.
It's gone again. Here we go. All right. My name is Fredrik Kahl. I'm a professor here at Chalmers. I'm going to talk about computer vision and deep learning, and in particular how deep learning has influenced my field. So I lead a research group here at Chalmers. We're a little more than 10 people. We do research in computer vision, machine learning, and medical image analysis. So here's an outline of my talk. So it's going to be deep learning and computer vision where we are now. So this is going to be a little bit of a survey of what's happening. These days you can sort of take the latest issue of Economist and find out what's happening in AI and computer vision. I learn a lot from undergraduates, students, and even teenagers about how self-driving cars work and so forth. So there are a lot of people knowledgeable about this. So this will be sort of a personal survey. I'm not going to be complete here or anything. And I'll also have spent some time on doing some reflections on the topic and what the sort of next challenges are in this field. So I'll give a bunch of examples, both from others and from my own research group, and then I'll conclude in the end. All right, so the basic problem is image classification. Sort of asking the question, is there a robin in this image? So this is sort of a question that's been around for a long time, and it's quite a complicated problem if you want to design an algorithm and sort of finding out where is the bird and sort of what kind of bird is it, etc., etc. Well, the way to solve it, this has turned out, is to use something called convolutional neural networks, which is a particular technique, a machine learning technique. So how do you do it? Well, I think it started with something called ImageNet. So ImageNet started about a little more than 10 years ago. There were some people saying, well, we need a big database of annotated images. So they started hiring a lot of people annotating images, saying there's a cat in this image, there's a dog there, and etc. Different classes. They have like 1,000 classes of different objects, which they classify in all images. So at one point in time, there were around 50,000 people involved annotating. So these are annotated by humans. And what they did is they organized a context or a challenge. And these are some of the results from this challenge. The winner, they announced the winner each year. So these are the sort of last couple of years. So in 2010, there were 28% failure rate on the images shown to the computer. And then it dropped. And then suddenly in 2012, it dropped quite drastically. And that was the first time someone applied successfully a convolutional neural net. So convolutional neural nets have been around for a long time, but suddenly it started working. And then, so it dropped quite drastically from 2011 to 2012, and then the next year in 2013, all the competitors in this contest were based on CNNs. And now, in 2016, it was down to 3%, and 2017, it's below 3%. And if you compare as a sort of average human on this database, or on this competition, you'll do about around 5%. So this is, I mean, above human performance, what they are doing there. So, I mean, how can you do that, you might ask? I mean, it's quite difficult to tell which kind of bird or which kind of dog it actually is in an image, and computers might be good at that as well. All right, so when I read this, well, I thought this is very exciting, but it's just a binary classification task, so not so interesting. Yeah. Is it a cat or is it not a cat in the image? Well, of course, people didn't stop there. They sort of said, okay, what if we have some heuristics to examine different parts of the image? Then we can use this technique for actually doing localization as well. And so this has been developed by a number of different these network architectures. Still, it's the basic CNN that does it. And of course, you can do it for different classes as well, cat, dog, duck, etc. And now you can do it very, very efficiently using, well, you can take out the contour as well. So it has happened, and this sort of development, I mean, it started in 2012 with this ImageNet competition. The first net was called AlexNet, and then it just have evolved dramatically. And now there are, so this technique has gone from sort of being novel 5 years ago to being quite mature. So it's really working, and it's fairly simple still, I would say, to use. So I was going to show you one example here of which is quite well known. Let's see if I can get it to start. No, well, yes. The question is. I don't get a pointer on that screen. Well, that's the problem. Here we go. So this is from CMU, where they apply their system for human pose detection in a YouTube video. And you can see this works in real time, and it sort of detects all the persons and a skeleton of it. So, yes. Right. This works quite well, and this is let me see how this. Here we go again. All right, so this works quite well, and you can just use it. The software is available online. That's also a new trend, that everything is open source, so that's very convenient. All right, so let me make some reflections on this. So a lot of things that happens quite fast, and you might ask, is everything solved and so forth? And I did my PhD in mathematics and sort of have this theoretical background, and thinking, so when I hear new PhD students entering the field with comments like this, I'm not so good at mathematics, so I chose deep learning. I sort of get a little bit worried. And then a colleague of mine, Viktor Limpetsky, he told me a couple of weeks ago. Before deep learning, it was difficult to keep page limits. I mean, we had all this theory we wanted to include in our paper. But after deep learning, we have nothing to write in the paper. So these latest papers, they have no equations whatsoever. It's just a figure of your network. So it's sort of really a bit depressing, and it's not only I that think this is a bit depressing. Nikos Paragios has a blog post on this deep depression of computer vision. So all the things we have learned and all the nice mathematics we know, I mean, suddenly becomes useless, you might ask. Well, it's not, I don't find it so depressing, really, but one might ask, is everything solved now? I mean, now you have these sort of real-time systems that does human-level performance recognition. Well, it's not. What I find is that these sort of simple network solutions, I mean, it's not simple. It's not easy to improve on the current state of the art. Now there's no more low-hanging fruit to be picked. So I think that's good news. Good news for us. Okay. So I'm going to mention some of the challenges we're facing with these deep learning methods. Well, what you want is not a binary classification task like saying, is there a cat or not a cat? You want something like getting out a whole skeleton out of a CT image. And that's what we call the structured output. It's some high-dimensional object. And we want to, I mean, in particular in medicine, we want to have some sort of guarantee that we get the plausible shape of the things we get out of the network. We want to include physical constraints, and we want to use our prior knowledge in these networks. And I think those are much open questions. How do you actually do that? So one of the things we've been looking at, I mean, is using other tools like Markov-random fields. So Markov-random fields is the statistical framework often used in image analysis, and combine it with these convolutional neural networks. And then you can do statistics and things like that on these networks in a nicer way. So yeah, it's moving fast here. We have already a survey article on how this can be done using Markov-random fields and in combination with deep neural networks. All right, another challenge is, I mean, how do you explain how these networks work? What's the theory behind? What's the mathematics of deep learning is something that interests me. So this slide has been left blank. So what's happened in the last 5 years has really been engineering-driven, application-driven, and not a lot of people know exactly what's going on in these networks. So I think that's a big challenge. Right. Something I'm interested in is in geometry. How do you sort of reconstruct geometrical models and things like that? So this is actually an old example. It's from the city of Aachen, where we have reconstructed a point cloud representation of the city. And the red spot here is where the images were taken. So that you can do automatically. And these are based on sort of optimization techniques and geometry. It uses no knowledge of what it's seeing whatsoever. So what we're interested in, how do you actually combine this with deep learning, the ability to recognize things at the same time? So we have a SSF project on how do you do this kind of reconstruction and simultaneously recognize what you're reconstructing? Because if you know you're reconstructing a building, maybe you should use some knowledge about that, and vice versa. If you know the shape of an object, maybe it can help you do better recognition and so forth. So when you can do that, you can do sort of visual inventory of a supermarket, for instance, and mapping of that supermarket. All right, so lastly, I thought I'd mention one thing that we're currently looking at, which is an open problem, I would say. It's visual localization. So we're collaborating with a bunch of people on this, not only from here from Chalmers, but all over Europe, really. So what's visual localization? Well, it's really, given that you have an image like here, you see on the left, you want to say, where was this picture taken? And so if you solve it, you can sort of tell exactly on the map or some sort of reference model where this image was taken. So this could be localization in a city or in the world and so forth. So this is sort of a basic problem. I mean, there are a lot of applications. Some say, well, you can use GPS. Well, it doesn't always work with GPS. You don't get very exact positioning from GPS, and you don't get orientation. So what are the applications? Well, augmented reality is one of them. You can sort of put in things into the picture if you know the exact localization. Well, you can also do VR. Here's a guy carrying around the Microsoft HoloLens. And if you can track that and have the exact localization, you can do virtual reality as well. Of course, navigation is an important problem. So I think the lawnmowers in a couple of years will look a bit different and have different capabilities than those running around randomly today. And of course, self-driving cars is an important application area. All right, so I say something. This is brand new research here, so I'll tell you some of the challenges with this. Here you see two different images taken at the same location. And it's really sort of challenging. If you built the model during summer and you want to recognize it during winter, how do you actually do that? Well, it's not really a solved problem. And there hasn't been any really good benchmarks for this, like the ImageNet or something like that. So what we started up some time ago is, how do you actually do benchmarking on this kind of thing? Where you have these day images and night images, you have seasonal changes, you have different environments, you have low quality images as well, and etc. You have suburban environments, etc. And how do you deal with all these sort of changes that are out there in the real world? All right, so we build this benchmark. So we took several cities. Here you can see a reconstruction of Oxford city. So we have Oxford, we have Pittsburgh, and we have Aachen in the benchmark. So we have these sort of 3D reference models, and then we have several hundreds of thousands of test images, query images, that you can test your favorite algorithm on these. So we have the camera pose for every of those images. And we have evaluate state of the art on this. So what can be said is that this is an unsolved problem, and this is something we haven't solved yet. We are making progress on this. I mean, a natural thing is to include semantics and these recognition capabilities that I talked about, because current state of the art is just based on geometry. We have some new results on this. This is from a paper we submitted yesterday, so it's very hot research here. So you have some examples of the database images when you built your reference model. You have the query image in the middle here, and then you have a segmented image as well. So the segmented image is just standard, one of these standard CNNs that segments out like road, sky, vegetation, etc. And if you use that kind of information on the right as well, you can really improve the results if you use it in a good way. There are lots of different numbers here. You shouldn't read them all, but it's this benchmark. But if you take on the left column here, you can see what sort of current state of the art does on this. They can recognize like 55% of the images if you require really high precision, like below 25 centimeters accuracy on your camera. But if you do include semantics into this, you can get much, much better results. This is in urban environments. If you look on the right, you get suburban and park, then I would say the problem is still unsolved. All right, this was just an example of some of the problems we're interested in. To conclude, so deep learning had changed a lot of things in computer vision. I would say there's no more low-hanging fruit. And the new challenges, if you want to improve, do require mathematics again. And, well, I've given you one example here, visual localization. So, thank you very much.
Questions? There's one at the back there. There's one at the back there.
Thank you for the presentation. I'm just wondering, is there any limitations or challenges you're finding regarding the deep learning models when you try to apply them to solve the questions or problems, for example, in your research?
Models? What kind of models?
Any challenges with deep learning models?
Deep learning models?
Yeah, I'm thinking like what would be the is there any, for example, limitations or disadvantages of the deep learning as a method when you are trying to apply it to your research work?
Well, there are different challenges. I think this structured output that I talked about, that you want something that delivers not only a yes and no answer, but something more high-dimensional, like semantic segmentation, or like the medical, in the medical image example I showed you. Here, I mean, how do you guarantee the output? I mean, that's a limitation of current sort of learning methods. They work quite well, but you cannot be sure that if you want to measure blood flow, that you actually get something reasonable. You can get answers that are sort of totally off. And that's still a challenge to sort of guarantee the correctness of your answer. And even uncertainty is a big problem with these models, I think.
Can I ask a question about image recognition in humans? When do you think that facial image recognition in AR, for example, our kids in the streets have facial image recognition in their mobile phones? When do we come that far?
When we have face recognition?
Facial recognition, when I can put my phone on your face and see who you are.
Well, I think the technique is already there. I mean, it's...
Yeah, I know, but when will it be in our iPhones or Android phones as an application?
Well, it's not really my expertise, but I think some of these phones, they do have face recognition capabilities. And if I look at the state-of-the-art methods for doing face recognition, they are performing better than humans, really. So it's just a question of, implementing it.
That leads towards some privacy issues with face recognition?
No, actually, I wasn't going that direction. No, I'm interested in when you said that the mathematics of neural networks, that you left it blank because it's not really explainable. And that seems to me like a huge problem, particularly in deployed scenarios where the decisions are going to impact people. There is even rules that say that you need to be able to explain how the decision was come upon. So my question is there a hope that there will be explanations for this?
Well,
I mean, what's the state of affairs in that?
Well, there are a lot of people interested in this, and there are people certainly trying to. There are interesting theories, so it was a bit provocative to put it blank there, and to some people, but there are certainly lots of research going on in this direction, but I don't know.
So is there a hope that we will be able to explain the decisions?
It almost becomes a philosophical question. What is an explanation? I don't know.
Okay, so I think we should go and have coffee now, and please remember to come back at 1500 hours, 3 o'clock, because that session will start at 15:10. So please have coffee and be back at 15:10. 15.